math correctly? Okay, I'm here. So 6.6, number 3.
Can you maybe do 6.523? He's doing, what are you doing? Is this 6.6 or 6.8?
6.3, number 3.
Okay.
Six, number 3.
Yeah, 6.6, number 3.
Sorry, I can't hear today. So you guys, suppose I have an ROC circuit in which the resistance is equal to 0 and the electromotive force is described by this function. Then let's talk about the limit of Q of T. Oh, I can't. I don't know what the solutions are. You said I can't. I don't know what the solutions are. I can say that 3 times.
So it tests the more.
It is. That is a square.
Solutions would be.
Sorry, I didn't catch that. So you guys do this for me. Jog my memory. How do we solve Cauchy-Euler DEs?
Step 1 is identify.
Step 1, identify if it's Cauchy-Euler. Is it? It's not. No. That is. Yeah. Michael.
For the very first term, the second derivative of Q with respect to, is that supposed to be T on that?
Oh, thank you. I'm so sorry. I've been too sloppy. I butchered the whole first term in numerous ways. Well, you guys, L and C are constants. If R is equal to 0, I think that middle term completely drops out. I think very clearly you and I can grab the solutions to this DE. I think the solutions are going to be the following. I said solutions. I'll back up. I meant the solutions for the corresponding homogeneous DE. In other words, in the homogeneous case, I think the corresponding underlying characteristic equation is R squared equals, can you guys help me? Is it 1 over LC? Being equal to 0. But if L and C are positive, doesn't it mean that R is going to be equal to plus or minus the square root of 1 over LC times I? Which means my complementary solutions are going to look like this. They're merely going to be, you guys, anybody? Say it again. So C1. Cosine.
Square
Square
root of 1 over L.
root of 1 over LC.
Plus C2.
C plus C2.
Sine of square root of 1 over LC.
Oh, wait, that's my complementary solution. What about the general solution? cosine of omega t.
plus b sine.
Well, I should say, assuming that my omega is different than 1 over square root of LC. Let's assume that. I think those are the solutions look like. And so I think in the end I've got a sinusoidal wave. And if I got a sinusoidal wave, then what do you think is going to happen as t increases that bound? All right, let me rephrase the question. If t increases that bound, since the solution is a sinusoidal wave, do you think I am going to get a limit that values a single real number?
No, it's just going to oscillate back and forth.
So I think that limit does not exist. By the way, you guys, only 10 minutes. My third flow up today. Sorry. Using your author's notation, he really meant Q of t, not yx. Again, I'm just not paying attention. That's all he's asking. Not a sophisticated question, but can you look ahead, see what the solutions look like, identify what that limit is? Under what circumstances do you think this could be true right here? Oh, did I answer the question? I just erased definitive. Let me check and reanalyze what he asked. My apologies, you guys. I just messed up. I thought his question was, what's that limit? It's not. He said the limit is this. I just didn't read the question. And now he's saying, if that really is the limit, then under what conditions is that going to happen? Oh, he gave it away. He told you. Man. He said, this is going to happen if omega is equal to 1 over LC under these square roots. Remember I told you the limit doesn't exist unless omega is equal to 1 over LC. He asked a different question. He said, suppose omega is 1 over LC. Why is the limit something different than what I said? Anybody?
There's no imaginary?
Oh, there is.
That's
Okay.
okay.
Imaginary numbers here.
Well, that's because there's no resistor, so how come R is equal to that, which R is really just another form of omega?
Yes, I do agree that this really is equivalent to omega. But I thought we were going to get sinusoidal waves over here. Why is it the case that he's saying this limit increased that bound?
Because you should change the particular to remove duplicity.
Yeah, because in the sense, if these two are the same, that means when I list my non-complicated solution, I've got duplicity. So I'm going to introduce a factor of t in here as well. And it's going to be a and b are non-zero. Well, actually, since that is my forcing function, at least one of those constants a and b is indeed going to be non-zero. So let me change the question to the way I read it. What can you say about this limit? If it is the case that we're assuming these two are not the same, that means I do not have this duplicity, which means that limit, like we discussed earlier, does not exist. Well, at least not as a finite fixed ring. Good. And what about something like 6.5, number 23? Here I'm actually given a differential equation, and it is this one. I have y double prime plus 2 times y prime plus 5y being equal to 7 times the sine of 2t. Where is the case that initially y is holds the value of negative 2 and y prime initially holds the value of 0? So question, determine whether the motion is underdamped, overdamped, or critically damped. How the heck do I answer that question?
I have no idea.
Well,
That's what got me.
guys, it really comes from the fact that when y prime is negative 2, and then when y prime is equal to 0, can you help? See, I don't think it comes in there at all. Yeah, I think it's irrelevant what the initial value conditions are. I think what's really happening is if you look at the corresponding homogeneous DE, and you look at the characteristic polynomial, which looks like this, is it not true that I get solutions that are non-real complex? Specifically, is that a -1 plus or minus, I'm sorry, I'm so slow, you guys have had a really bad day. B squared minus 4AC. So that'd be a 2, I think, I. That being the case, I think my complementary solution is simply going to be this. Yes, t's. I'll use t's. Is that going to be an e to the negative t times c1 cosine of 2t plus c2 times the sine of 2t? Ah, shoot, look at that, you guys. That's clearly under damping, because now I've got an oscillating wave that's bounded above and below by an exponential function that's decreasing. Did you guys agree? Well, the top one's decreasing. So I think clearly it's under damping. I think if I'm asked to find a solution to the initial value problem,
Can you
and
graph that really fast? Just show us pictorially.
Can I make up some numbers for C1 and C2?
Absolutely.
And if I were to, you guys allow me this, to set C1 and C2 to be equal to 1. You know, Bradley, can I take that back?
Yeah.
Can I just allow C2 to be 1? And I'll allow C1 to be 0. Because I think then I simply have y of t being equal to e to the negative t times, did I choose the sine function? Now I gotta confess, if this were a sinusoidal wave, the period of the sine wave is going to be positive pi. It's going to look like this. Do you guys agree? However, because the amplitude is not constant, it's variable, I think what's happening is I'm getting this oscillating wave that's bounded above and below by an exponential function. And I think that exponential function looks like this. But also it's negative. Oh, and by the way, this is still pi. This is still 2 pi, I agree. Now I can't subclassify this as a sinusoidal wave because the amplitude is not constant, but that would be the graph of this oscillating wave, bounded above and below by the enveloping curves, y equals plus or minus e to the negative t.
What would something that is overdamped look like?
Overdamped is going to look like this, generally speaking. Here's my t-axis. Say, for example, I pull down a string, and the string is so darn stiff, it doesn't pass through the resting position. And if this is the resting position, if I pull a spring down, it's so tight it just comes back to its rest position. It just has a vertical displacement that looks like that. Or maybe it's not quite that stiff, and it does oscillate only a tad bit, meaning I pass that equilibrium position, and I come back to the resting position.
Yeah, what about critically?
Graphs are going to be the same.
Same? Okay.
Very simple. So I think the really interesting one is the underdamping.
Okay.
So everybody, there is another part to the question. So find the solution of the given initial value problem and identify the steady state and transient parts. You guys, only because the vocabulary is interesting, do you mind if we finish?
Okay.
Just one. I'm not trying to put you to sleep. But I do think I've got the comprehensive solution. That's done. As far as the particular solution is concerned, I'm going to try a particular solution, which involves a times the cosine of 2t plus b times the sine of 2t. Now, picking this up off the input, slap it into original dE. What do I do next? What do I do next, Mike?
Differentiate the particular solution to get our parts for the differential equation.
Oh. Okay, that's not what I was thinking.
Or just plug it in the equation set equals to the 17 and solve.
I think just the thing I should do first. What is that?
Oh,
What's that?
check for particular.
Thank you. Fixed a mistake. Is there any duplicity? Yeah, there is. So I'll fix it. I'll insert an extra factor t. So as suggested, differentiating. All right, let me change my words. I'm the one doing the work. So differentiating. You know me, I'm lazy. Differentiating. was hoping you say give up. It's too much work. So maybe instead, can we just pretend it's a complex value forcing function? Which means my z sub p, oh shoot, this is going to be so much nicer. It's going to be nothing more than a times t, and then e to the... Did I walk in the right room? You guys, old business. You guys are giving up. 2it.
Yeah.
Alright, and differentiating I think is just going to be so much easier. Z sub p prime is going to be, well, here's the first times the derivative of the second. Whoops, I lost my room. Just a minute. I said, here's my first times the derivative of the second. Plus the second times the derivative of the first. The second derivative is going to be, okay, I'm going to give up on this pen.
Professor Valentine,
Yes, sir.
why did we remove duplicity on that? By adding the factor of t?
Well, I was duplicating what I had. Oh, yeah. My apologies. When I wrote it down, I didn't even see the first factor. You guys, I'm just a mess all around today. I'm sorry. So I think in this example, I really don't have duplicity. It's not going to work. And since I don't have duplicity, I made a mistake. I guess I don't get that factor t in there. All right, I've already considered complex value solution, so let me just stay with it. Derivative, piece of cake. Second derivative, still a piece of cake. Picking this up off the ink board, making my life so much easier, slapping it back into the dE. I now have the second derivative is being added to 2 times the first derivative. That's being added to 5 times the original. And all of it is equal to my forcing function. You guys, I'm tired. I took a break. I suppressed the factor of e to the 2it on both sides. Factoring out my a, I suppose that means, is that a positive 1 plus 4i times a is equal to 17? Wow, these numbers are nice, aren't they? That means a is equal to, is that 1 minus 4i?
Yeah. Yes, that is.
That being the case, let me pick this up off the ink.
You divided and then multiplied by the conjugate.
What's that?
You divided and then multiplied both by the conjugate, right?
Yeah, it's just that downstairs 1 minus 16i squared has to be 17. Got some cancellation. Got real lucky with the numbers. You guys yell at me if I'm skipping too much, please.
Can you show just...
Yes, I can. That's what I'm saying. Just vote me. I could be wrong. Let's check it. Is that a 17 over this?
Yes.
Now multiply top and bottom. This is math though.
D.
Yeah. Now downstairs I get my 1 minus 16i squared. Oh shoot. That's the same thing as 1 plus 16. That's the same thing as 17. Oh, but upstairs I get 17 times binomial. 17 times stuff. 17 times stuff is just that now I get to do some cancellation. Now you get let's see how many pens I can go through in 2 minutes.
You see the big ones on the board right there next to the pencil.
Right there.
Oh yeah, I was looking for a black.
Okay.
So you guys, 1 minus 4i is my coefficient. I'm running out of room. Can I come back over here? Can I erase? So I'm nothing too sloppy. That means z sub p is going to be my a, which is 1 minus 4i. Times my e to the negative, or e to the 2it. Isn't that just cosine of 2t? Plus I times 2. Bless you. But doesn't that suggest that y sub p is in the end going to be nothing more than negative 4 cosine 2t? I don't know what else. Is it a positive sine 2t? I just don't want to move on unless everybody sees where I'm at. Michael?
So from going from Z key to Y key, distributing the 1 and the negative 4i, you would get basically the first sine 2t plus I sine 2t, and then you would get a minus 4i cosine 2t, minus, or plus 4 sine 2t.
Yes. And I simply took the imaginary component. Because the original forcing function in the real valued situation involved a sine function, I over here took the imaginary component of a complex valued solution. All right, as long as you see it. That being the case, I think my final solution to the PE, if I can continue to erase, is going to be of this form. Y of t is going to be equal to my compromise solution. Minus my 4 times cosine of 2t plus sine of 2t. So you guys help me out with this. How can I find the values for C1 and C2? You have the initial value conditions. I'm going to plug 2 and 4 y, 0 for t everywhere. I'll build an equation involving 2 unknowns. Actually, in this example, only 1. I can solve for it. Now to find the other, I take the solution and differentiate once, and then again use a second initial value condition.
So for this, when we're plugging in the second initial value, so we can either take the derivative of the original equation or go from the solution of the first one and take the derivative of that.
The solution to the first one. What do you mean by the first one?
Plugging in the initial condition for y, where t is 0, into that equation, getting something, and then taking the derivative, we can plug in the second initial condition.
Unfortunately, I can't do this. I can't plug 0 for t and then differentiate because we don't do no independent variable.
Okay.
So when I said plug 0 for t and negative 2 for y, you generate one equation and potentially 2 unknowns. All this example, it only goes out one unknown.
Okay.
And basically what's going to happen is you find a value for C1. Now, if I were to differentiate a second time, this as you're reading it, differentiate this function one time, then I can use a second initial value condition.
Okay.
You guys help me with this. For large values of t, what can you say about this component of my solution? It goes away. Also classified as my transient solution. Of course, as t increases that bound, this term does not go away. I admit it's an oscillating wave. That's actually a sinusoidal wave. It's just that that's what I'll refer to as my steady state solution. Because it does not go away for large values of t. Are you with me? Yeah. So you mind if I skip the arithmetic of finding C1 and C2?
So you just have to look at the limit in order to figure out whether it's transient or steady
In a
state.
sense, I wasn't even being that careful. I just realized with this particular coefficient up front, not that it's a constant coefficient, it's going to force the whole thing to go down to 0.
Okay.
It's not that I'm being really careful in valuing limits. It's just an observation.
Okay.
And you want to dive into 6.8. Number 9. Still that bad Beatles song. Where I have y double prime plus 2y prime plus y being equal to nasty business. Oh, jeepers. The author says, he adds this, that x is strictly positive. Why did he say
Wait,
that?
this is 6.8, number 9?
Oh, it's not. I'm so sorry.
I'm on 6.8 here.
I'm doing a typical mistake. I'm just looking
Yeah.
at the number up top.
I do that all
It's
the
the
time.
next section. I do it a lot too. No, I like this question. I won't do any writing. I won't continue. But the author says this. Why?
Huh?
Why did he say that?
Have Have we even gotten to this part yet?
I hope
Have we
so.
done
Isn't this just
6.9
variation of
is
parameters?
reduction of order? 6.9?
Should be on
Well, we
That's
should be.
6.8.
Well, 6.8, number 9
page
is
523.
page 523. It's a completely different question.
No, I know. I read the wrong one. Now that I got it up there, can you just talk about it for a minute?
Oh, okay.
Why did the author put this in?
The natural log of x doesn't exist.
Because one over
See, I
x
think for that reason,
Yeah.
he shouldn't have put it in. It's just kind of understood with the
yeah.
forcing function.
Yeah.
I'm sorry.
Okay.
But you're right, I'm in the wrong section.
Okay.
And now that I get my act straight, you said number 9?
Mhm.
I have instead this differential equation. And I'm asked to actually solve the DE. And to solve it, using my characteristic equation, r squared plus 1 times r minus m squared equals 0. And if I use the quadratic formula, I get. You guys, do we have an exam coming up soon?
Next week.
Thursday.
Like I said, if I solve this characteristic equation, given that we have an exam next week, what do I get? A mistake.
Yeah.
Because this DE does not have constant coefficients, that's not the characteristic polynomial. Did you guys see it? Alright, so I blew it. I guess be more careful then. Let me go ahead and make a substitution. If I allow x to be equal to the e to the t, then I think I do transform, no tricks this time, this DE into one with constant coefficients. I think the coefficient for y double prime would be 1. I think the coefficient for y prime would be 1 less than this, which is 0. Oh shoot, isn't that a piece of cake? By the way, I said y double prime. I'm looking at the corresponding DE, which really has this in there. But what's the corresponding characteristic equation? R squared minus m squared equals 0, which means r is equal to plus or minus m, and by the way, assuming m is a positive value, standing for mass, I assume, then I think what I have are 2 distinct root solutions. Yes, Chris?
Wait.
Can you show me how you got that y double prime minus m squared y?
Yeah.
Where does the e to the t go?
And where'd your y prime go?
Well, I think if I have a DE that looks like this, x squared y double prime plus a 1 times x y prime plus a 2 times y being set equal to 0. If I do indeed commit myself to this particular substitution, is it not true that the DE transforms into this one? That y double prime plus 1 less than a sub 1 times y prime plus my a sub 2 times y is set equal to 0. 1 yes.
Cauchy.
Cauchy.
Just like for the exam, how much
What's that?
when you do that?
Oh,
Is it-
absolutely nothing. I think I wrote too much in the board. You might not have bothered with the substitution. Well, you could, because I think your author has a different approach. I just don't think all that work in that section, that was a big section, is so unnecessary. If you just commit to the substitution, I think you're done. Michael?
I'm still not sure, like, when you have an x equals e to the t, is that turning like x squared into e to the 2t, or is that an initial? And then, how's that, are you dividing it out? Well, I guess the intermediate step between x squared, y double prime, a1.
I got an idea, you guys. Why don't we just not look at this problem? I want you to take a break. And I just want you to let me play for a minute. I want you to consider a differential equation, as in this form right here. Because apparently you're missing something. And here's what you're missing. If I want to take a peek at what dy dt looks like, hold on, I'm jumping around too much. Look at this dE and let me commit to the substitution. Now I'm going to ask a simple question, what's dy dt? Well, when you look at this relationship, I don't know, it's got something to do with the dE up there in terms of x's, where x is being replaced with this expression. So maybe I can think of, this is nothing more than derivative for y with respect to x. Oh, I can't, darn it. means x is equal to t. But I can allow dy dt to be equal to dy dx as long as I multiply by dx dt. That's just a chain rule, you guys. And by the way, what's another name for the second factor of dx dt? Well, that's just going to be e to the t. But you know what? I don't like it. Can I rewrite that? Because I think another name for e to the t is x. So I think dy dt could be interpreted as x dy dx. You know what that really means? It means I can take my dE and I can replace this middle term right here, this x times dx dt. I can replace it with a dy dt. You guys think that's slick? My second term isn't going to change. I just get an a sub 2 times y as a function t now, not x. Being set equal to 0. Oh shoot, I messed up, you guys. Darn it. I need to come up with another name for this first term. But before I do, appreciate the fact that with the substitution, I replace the second term with another second term that has no factor of x or t. It's a constant coefficient term. Maybe if I finagle this a little bit more, maybe I can massage this to e so that this first term no longer has a non-constant coefficient. Let me give it a shot. I think to come up with a second derivative for y with respect to t might be considered the first derivative with respect to t of the first derivative. Or shall I say, I've got the derivative with respect to t of, let me just give dy dt an alternative name. What was it? Was it x dy dx?
So I'm just looking back here, right, at the other problem. Your x times y prime, that's just your x dy dx.
It is.
So what did you do with it right there? That's when you got rid of it.
Here?
Yeah.
Well, since that was your question, I want to talk about theory first. I want to show you how this equation transforms with the substitution. Then you clearly see why that term completely drops out.
Okay.
So you just let me play for a minute.
Okay.
And diving in, are you guys ready for me to apply the product rule?
Probably not, because that's normally the answer when you do that.
You know me too well. Yeah, I think I'm not going to differentiate because that's in terms of x. Oh shoot, I'm differentiating. I'll fix it. Using yet again another application of the chain rule. D of something with respect to t is the same thing as d of that same thing with respect to x. dx dt. It's just that. Now using the product rule where I can, I think I've got the first times the derivative of the second plus the second times the derivative of the first times my dx dt. Oh, you know what? Another name for dx dt is it's just going to be x dy dx.
That's dy dt, not the x dt.
My apologies. My goodness, I made a mistake. What is dx dt? I thought it was dy dt. What is dx dt? You guys e to the t, which has another name of x. Let me clean up. Rewriting, I think it says the second derivative for y with respect to, if I get my letters straight, t, could be interpreted as nothing more than x squared second derivative for y with respect to x, plus my x dy dx. But you guys give me another name for the second term on the right hand side.
dy dt.
Yeah, I agree with that. I think another name for this term right here is just dy dt. Or how about, if I rewrite that, I think that means the following. I think it means the x squared second derivative for y with respect to x could be interpreted as nothing more than the second derivative for y with respect to, well, the new variable, minus my dy dt. Oh shoot, you guys, check this out. Look what's inside the circle. I'm going to pick that up off the ink board and slap it in for an x squared dy dx twice, wherever I see it. Oh, I see it right there. That gets liberally replaced with nothing more than second derivative of y with respect to t, minus my dy dt. Oh, but shoot, you guys, look at those two terms. They're like terms. I'll combine them by addition. And I think I've got the second derivative for y with respect to t, plus my a sub 1 decreased by 1 times dy dt, plus my a2 log. Did you guys clearly see with the substitution, to transform this non-constant coefficient d into one that is constant coefficient? With that substitution, I naturally subtract 1 off the coefficient for y prime. Do you see it, Bradley? That being the case, this coefficient 1 is replaced with 1 minus 1. It's 0 and drop down. Now that you believe me?
Yeah.
And now that this is a constant coefficient d, I have a mathematical legal right to look at the characteristic equation, and here are the two math d solutions to that characteristic equation.
So when we go from y being in terms of x to being in terms of t, previously we've written the second derivative of y as d2y over d squared. Is it okay to just use y double prime, even though it's now like a different y?
Yeah, I don't mind as long as you keep it straight. I mean, I did,
Okay.
because I thought it was assumed. But yeah, keep in mind that it is a function of t, and so when I actually do come with the solution, I better back substitute. Since the original dE was posed in terms of y as a function in the variable x. So be careful. Well, that being said, I don't know if I've answered the question. It's been too long. Oh, I haven't solved this dE. Jeepers. And to solve this dE, can I get rid of this? I think in the end it simply means that y as a function in the variable t is going to be nothing more than c1 times e to the mt plus c2 times. Oh shoot, like I said, we got to back substitute. I guess that means that y as a function x is going to be nothing more than, oh really?
C1M.
Is that okay? And we solve the dE. Whoever asked. All right. Tell me if I can clarify something.
Can you just show?
Yes.
Can you just show the step where you
Of
set back
course.
substitute?
Yeah.
I'm simply saying this. I got c1 e to the m times t, don't put the t in yet, plus c2 times e to the negative m times t, don't put the t in yet. But you got to confess, with this substitution, isn't it the case that t is a natural log of x? And I maintain then that this t and this t right here can be re-expressed as a natural log of x. Now, using my properties of logarithms, I think I can bring the m up in the exponential position. It's just because these two functions are inverse functions of each other, they cancel each other out.